Hello, and welcome to Math 120 Final Exam Review. This will cover rationals and some extras that I couldn't find a good place for, so they're going here. My name is Tuesday J. Johnson. I'm a lecturer at the University of Texas El Paso and an assistant professor at Doña Ana Community College. This particular review is for Doña Ana Community College. Math 120 is Intermediate Algebra. You can find a copy of the review that these problems reference at dacc.nmsu.edu/math. If you look on the right side menu, there's something that says Final Reviews. Click there, and you'll see a list of all of the courses that have the math final reviews posted. So when I refer to numbers or calculator versus non-calculator, it's all explained in that handout. So, in these videos, I've included this little icon over here. It's actually two, but no calculator. So any problems that have the no calculator designation, you will not be allowed the use of a calculator on the exam. Now, you won't need a calculator for most of these problems as well. So the numbers are really nice. They work out. On portions of this video that do not have these symbols together, you are allowed the use of a calculator. So the exam comes in two parts. So, number 17 in the no calculator section, state the domain for each function below. Remember that a rational function, a ratio of two polynomials, has a domain that includes all real numbers except values that make the denominator 0. We can never divide by 0, so we can't have a 0 in the denominator. So what I like to do is I take the denominator, x squared minus 2x, and set it not equal to 0. I can use the zero factor property, whether it's equal to 0 or not equal to 0. The same type of thing applies. I'll factor my left-hand side, x squared minus 2x. I'm comparing to 0. They have an x in common, so I factor out the x, and I'm left with an x minus 2 in the parentheses. Still not equal to 0. This tells me that x is not equal to 0, or x minus 2 is not equal to 0. And if x minus 2 is not equal to 0, then x cannot equal 2. So I did skip a step right here, setting the denominator not equal to 0, factoring, and then setting each individual factor not equal to 0 will give us our two answers. Let's try it again. Part B. F of x equals 4x minus 16 over x squared minus 16. It's super tempting to want to cross out those 16s and hey, I could cancel an x. No, you can't do that. You cannot cancel from anywhere in this entire rational expression unless you could cancel it from everywhere. I'm going to say that again. You can't cancel anything unless you can cancel it from everything. So there are four parts. The numerator has two parts separated by the minus sign, and the denominator has two parts. We can't cancel the 16s because the 16 is not in all four of these terms. But we again take the denominator, x squared minus 16, and say it cannot be 0. So I'm comparing to 0. Then I factor. X squared minus 16 is the difference of squares. That is x minus 4 times x plus 4, not equal to 0. And solving each individually, if x minus 4 is not 0, then x cannot be 4. If x plus 4 is not 0, then x cannot be negative 4. And we assume that the domain is everything else. It's all real numbers such that x is not these specific values. Now we're going to take those same functions and we're going to do something else with them. Simplify the right side of the following functions. Same function, f of x equals 6x minus 12 over x squared minus 2x. We will only simplify the right side of rational functions after finding the domain, but we already did that on a previous slide. Now that we've found the domain, we're going to factor the numerator completely. They have a 6 in common, so I'll take out the 6. I'm left with an x minus 2. We already factored our denominator, x squared minus 2x. They have an x in common. I'm left with an x minus 2. The x minus 2's in common, they will cancel out. Some people get some enjoyment in being able to cross out their math, so there you go. And the result is 6 over x. So I've simplified the right-hand side of the equation, of the function, excuse me. If f of x is 4x minus 16 over x squared minus 16, in order to simplify, that's a fancy way of saying factor and cancel when it comes to rational functions. 4x minus 16, they have a 4 in common. When I take out the 4, I'm left with x minus 4. X squared minus 16, we already saw, simplifies into the difference of squares. And x minus 4 in the numerator will cancel with the x minus 4 in the denominator, leaving 4 over x plus 4 as our simplified version of the right-hand side of this particular function. Factor and cancel. Anytime you're simplifying a rational expression, factor and cancel. Perform the indicated operations. Simplify the result. Keep in mind, this is still a no calculator problem. Number 19 has 4 parts to it, and we're going to do all 4 of these one at a time. So let's look at subtraction. If I have y squared minus 6 over y squared plus 9y plus 18, and I want to subtract y minus 4 over y plus 6, the first thing I have to do is find a least common denominator. It doesn't have to be the least common denominator, but this is the least amount of work that you'll have to do later if you find the smallest denominator now. In order to find the least common denominator, I'm going to factor all of my denominators. Y squared plus 9y plus 18. I'm looking for two things that multiply to be 18. Because that's a positive, they have the same sign. This tells us the sign is positive. Multiply to be 18, add to be 9. That's going to be y plus 6 times y plus 3. The second denominator is just y plus 6. Nothing to factor, so my LCD happens to be y plus 6 times y plus 3. Now I know my common denominator, I'm going to multiply so that both of my rational expressions have that denominator. Now we already know the first rational expression has the common denominator, so we multiply the second expression by y plus 3 over y plus 3. We multiply by what was missing. Notice there's no equal signs here. Because there's no equal signs, we have to keep our denominators. This is not a time where we can cancel them out. We're getting common denominators so we can compare equal sized pieces of whatever. So on my first rational expression, I'm going to call this a fraction, even though it's a little bit of an abuse of the term. Y squared minus 6 over y squared plus 9y plus 18. That one stays the same. Minus, and then I'll distribute. I'll use FOIL. I have y squared plus 3y and a minus 4y makes a minus 1y. And minus 4 times 3 is minus 12. In my denominator, I could multiply it out. I know what it looks like. Or I can leave it factored. I'm going to need it factored in a minute anyway. Once we have common denominators, same denominator for each of the two fractions, now all I have to do is combine my numerators, making sure to distribute the negative sign. So this is y squared minus y squared. They cancel out. I have no y's over here, so I have minus a negative y, giving me a plus y in the numerator. Negative 6 minus negative 12. So that's negative 6 plus 12, which gives us a positive 6. And remember, when you're adding and subtracting fractions or rational expressions, you keep the denominator the same. You only combine the numerators. As I'm looking at my completely factored form, numerator and denominator, they have a common factor of y plus 6. Some of you might want to factor out a 1 so that you can see where our 1 in the answer comes from. So those are parentheses, not absolute values. They just don't look like it. So cancel the y plus 6's. Keep the 1 in the numerator to say, hey, I have a fraction. 1 is a factor of everything, so it factors out. And the y plus 3 in the denominator as well. Simplified version is what we're going to be looking for. Now let's try an addition problem. 2x over x plus 2 times x minus 3 plus x over x plus 2. The nice thing about this one is it's already factored for us. We see our first denominator is x plus 2 times x minus 3. Our second denominator is x plus 2. So I can see immediately that I need to multiply the second fraction by x minus 3 over x minus 3. And so I do just that. I leave 2x over x plus 2 times x minus 3 plus I multiply x over x plus 2 times x minus 3 over x minus 3. Distribute the x. X times x is x squared. X times negative 3 is a negative 3x. Denominators, I'm just going to leave them in factored form. Because we're adding, it's just straight up addition. 2x plus x squared minus 3x, a 2x, and a minus 3x give me my negative x. I have an x squared. In order to see if we can simplify this at all, I'll factor my numerator completely. X squared minus x is the same as x times x minus 1. Notice no factor, x or x minus 1, from the numerator is also present in the denominator, and so this is a fantastic answer. I would accept this one as well, but many instructors would like to see the factored form just to show that, hey, I checked, nothing cancels, I didn't accidentally get it right, stopping early. Now we're going to divide. V plus 5 divided by v squared minus 6v minus 55 divided by all of v minus 8 over v squared minus 4v minus 77. For multiplication and division, you don't have to have a common denominator. For a division problem, not only will we factor every single thing, but we are going to change the order. We're going to change this division to a multiplication, and we're going to take the numerator and put it in the denominator. Our denominator, v squared minus 4v minus 77, we're going to factor, and that becomes the numerator. So in order to divide, we multiply by the reciprocal. So we'll flip it over. V plus 5, fantastic, v plus 5. V squared minus 6v minus 55. Now, I see the v squared, so I know I'm going to have v times v. 55, and it's a negative 55. So I know one of the factors is positive, and one is negative. It's the only way you can multiply to get negative. The first thing that comes to me in 55, since it's repeated numbers, is 5 times 11. Hey, what do you know? 5 and 11 are 6 apart. So this actually factors in a straightforward way. But which one is negative and which one is positive? If the last sign is negative, it tells us our two factors have opposite signs. And if the first sign is negative, it tells us the bigger one happens to be negative. So if my factors are 11 and 5, this tells me that the bigger one is negative, so I have v minus 11 times v plus 5. We could do a similar analysis here. To get 77, my first thought is 11 and 7. 11 and 7 are different by 4, so I'm going to have v minus 11 times v plus 7 over v minus 8. Remember, division turns into multiplication by the reciprocal, so I just flipped it over. Now, the cool thing about multiplication and division is we never actually multiply or divide. We're going to cancel common factors across the fraction bar. Here I see a v plus 5 in my numerator, a v plus 5 in the denominator. I'm going to cancel it. In the second rational expression, the v minus 11, there's a v minus 11 in this denominator. As long as I'm across the fraction bar, no matter which piece it's from, cancel a numerator with a denominator factor, it's all good. So when I cancel out my v plus 5s, my v minus 11s, all I'm left with is v plus 7 divided by v minus 8. And without even ever multiplying or dividing, we've divided these two rational expressions. It's a fancy way of saying factor, write them next to each other, cancel, and simplify. Now, the easiest type of problem, multiplication, you don't have to get a common denominator, you don't have to multiply by the reciprocal, you just factor and cancel. We save that one for last. So 2n plus 6, if we want to factor that, factor out the 2, I'm left with n plus 3. In the denominator, I want two things that multiply to be 15, and they add to be 8. I know they're the same sign, they're both positive. So 5 times 3 is 15, 5 plus 3 is 8. I can factor as n plus 5 times n plus 3. In the second rational expression, factor a 3 out of the numerator, 3 times n plus 5. In the denominator, n squared plus 11n plus 28. Two things that multiply to be 28 are 7 and 4. Look at that, 7 and 4 add to be 11, so it works out. So n plus 7 times n plus 4. Again, we'll cancel common factors. We can see that n plus 3 in the numerator cancels this n plus 3 in the denominator. And n plus 5 in the numerator cancels the n plus 5 in this denominator. I don't see any other common factors, so now we actually get to multiply. 2 times 3 is 6. Denominator, I have neither of these two. That's n plus 7 times n plus 4. And you don't even have to multiply those out. You can leave it exactly like that. Now, the no calculator problems are gone. That's fantastic. That's not true. This is also a no calculator question. I just remembered. I forgot to put the logo. But you're not going to need it. Probably. So you're going to be given a problem. Possibly. And this is from the review. It's one problem in 3 parts. So tables of values and scatter plots for 3 functions are listed. And they look a lot better, actually, in the review, but I did what I could here. For each function, we're going to identify if it's linear, exponential, or quadratic. If the function is linear, we're going to find the slope, m. If the function is exponential, we're going to find the base multiplier, b. These are the key identifiers of the functions. If the function is quadratic, we're going to find the vertex. So, if I look at the shape of this graph, it looks like it's definitely not a straight line anywhere. And I don't see it changing. Maybe if I had the second half, I'd have a different opinion. But to me, this looks exponential. Based on the shape, I'm thinking probably exponential. But look what I have over here. How do I go from 6 to 18? Well, I can add 12, or I can multiply by 3. But if I add 12 to 18, I don't get 54. But if I multiply 18 by 3, I get 54. And then I would try it again. 54 times 3, 162 times 3, 486 times 3. And I notice that I do have a pattern that I multiply by 3 to get my next y value. Therefore, I'm expecting this to be exponential. And my base is 3. The constant term that I multiply to get the next y value as x increases by 1. Same instructions, everything up here is the same. As I look at this scatter plot, that looks like a straight line. That looks like it's pretty easy to fill in as a line. So based on the shape of the plot, it looks very linear. I look over here. To get from 9 to 6, I subtract 3. Now I've already answered exponential, so this one can't be exponential. It's either quadratic or linear. Let's take a look. From 9 to 6, I subtract 3. Subtract 3, subtract 3, subtract, hey, look at that. I subtract 3 to get the next y value at each step. As x increases by 1, y values go down by 3. The graph is a line, it's linear, decreasing by 3, so my slope is negative 3. Decreasing, negative, by how much? 3. If I were adding 3 each time, I would have a plus 3. If I subtract 3 each time, I'm going to literally say m is negative 3. That's how much y changes by as x increases by 1. Now my first one was exponential, my second one's linear, this one has to be quadratic. But let's see why. As I look at my plots, oh yeah, it looks like this changes shape, right? Not changes shape, it changes pattern. So it goes up, and then it comes down. And we know the graph of a parabola is the graph of any quadratic. And so if we have a turning point, this is probably going to be our vertex. Let's take a look at the values. See how 3 increases to 6, increases to 7, and then it starts decreasing again? From 7 we decrease to 6, decrease to 3, decrease to negative 2. So it's not necessarily a consistent pattern, but it changes direction. So we're adding, and then we start subtracting. So we're increasing, and then we're decreasing, and that's how we know that it's quadratic. So where does it turn around? Well, here's a 3, here's a 3, here's a 6, here's a 6. This 7 is right in the middle of where it turns around, so my vertex is the point 2, 7. Alright, the shape of the graph leads us to which one? If it's linear, we find the slope. How much do we consistently add or subtract to get the next y value as x increases by 1? If the function is exponential based on the shape of the graph, the base multiplier b is the amount that you multiply by to get the next y value as x increases by 1. And if the function is quadratic, we're looking for the turning point. Where does it turn around? Where does it change direction? All right, some of those extras I mentioned, some rationals plus. If we have this particular graph, this is very exponential looking, We want to estimate f of 1. See how the 1 is inside the parentheses? What goes inside of an equation? X does. That tells us that the x value is 1. Alright, when x is 1, my graph says that y is 20. That means that I'll say f of 1 equals 20. An input of 1, an x value of 1, gives me an output of 20. We want to estimate the x value that makes f of x equal to 10. Let's see. Estimate the x value. So I don't know x. I know that f of x is the same as y. If y equals 10, I'm looking right here. Oh, where does that happen? My x value, it looks like that's going to be 2. What point is the vertical intercept? The vertical intercept is where the graph crosses the vertical axis. Right there at 0, 40, and it says here a point, so I'm going to put it in point form, 0, 40. State the domain and range. Looking at this particular graph, it doesn't look like anything weird happens with x. It goes forever to the right. It comes from forever to the left. It looks exponential, so I'm going to say the domain is negative infinity to positive infinity, also known as all real numbers. And it looks like we're trying to get a range of 0 to infinity. I don't think it touches 0. Based on what I see with the graph, this would be my impression. So that's what I'm going to go with for the answer. Let's take a look at one more graph. These are the bonus. These are the extras. This is also a no calculator problem, but did I need a calculator? No, I need a finger so I can follow the lines and find the certain values. Here we go, nice little absolute value graph. If we estimate f of 9, right, input of 9, and output, what's my output? So when x is 9, it's about here. My y value looks like 4. Therefore, my estimate is f of 9 equals 4. When x is 9, y is 4. Estimate the x value or values that make f of x equals 6. Yet again, I want f of x to be 6. That's a fancy way of saying my y value is 6. We're going to pretend I could draw a straight line. That's definite big imagination there. But we can see that this x value of 10 gives us a y value of 6, and this x value of 0 also gives us a y value of 6. Did I say that right? I think so. Estimate the horizontal intercepts. Horizontal intercepts. Horizontal axis, that's the x-axis. Where do we cross? Right there. Right there. I'm thinking that that's at 2, 0 on the left. 7, 0, close enough as an estimate for my horizontal intercept on the right. For part D, the domain of this function, notice how the domain, the function gets wider and wider, so it keeps going all of my x values to both to the left and to the right. My domain is all real numbers. My range, I have to trust my arrows. The arrows say it goes forever up. It's never going to change direction again. So my range, I look from the bottom up. The first value I hit is -6. And then the arrows indicate that I will take on every y value above -6. So -6 and above. Bracket on the -6. Parenthesis on infinity. So that's rationals plus. Finding the domain of a rational function. Simplifying rational functions, and then add, subtract, multiply, and dividing rational functions. And then taking a look at some graphs and how to read them. And looking at stat plots and table of values to determine linear, exponential, or quadratic. Thanks for listening.